I mean, don't feel me. Reach a lot of things. But it doesn't take long to turn it into a liquid. So even our solid fats are pretty unsaturated. Finding a hunk of like pure saturated fat would be like hard as a brick. We don't really see those too much naturally. They're almost all mixed, almost all have some amount of unsaturation.
Almost like Crisco. Crisco is a lot harder than...
Yeah, Crisco is about 30% unsaturated. If you got to 0% unsaturated, like seriously, it would be like a brick. Be more like plastic than food. Doesn't that sound good? Good so far? So almost all fatty acids are actually in the form of triacylglycerols. And that's where a fatty acid reacts with this structure, glycerol. And I want to take a moment to sneak ahead, because next chapter, we're going to be reminding ourselves about organic reaction mechanisms. So let's take a look at glycerol reacting with a fat. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Let's get some 12:0. And let's get glycerol. So, if we have some fatty acid and some glycerol, and we know they're going to react together, first pro tip, we're probably going to have to draw arrows that from a purely organic perspective don't look great, because we're going to assume there's an enzyme doing things like deprotonating or having magnesiums to stabilize things. This is an enzyme catalyzed reaction. It does not happen in a vacuum. If you take a bottle of free fatty acids and a bottle of glycerol and shake them up and do the hokey pokey, they don't react. You need an enzyme to catalyze it, so we're going to allow ourselves some leniency and like, well, that's kind of a cruddy nucleophile, but let's do it anyway, right? Because we're going to assume there's going to be some aids. But if we look, we need to start thinking of how do we think about these mechanisms. And again, for 95% of biochemistry, you will not go wrong if your first question is, where's my electrophile? And your second question is, where's my nucleophile? So if we look at this, where is our best electrophile that we have available? Our carbonyl, specifically the carbon in the carbonyl. This oxygen has a lot of electron withdrawing going on in 3 ways, 3 bonds worth. This carbon is left very, very delta positive. Not a full-on positive charge. We're not going to go as crazy as a carbocation or anything, but it's delta positive. So I've got that. Then I'm going to ask the second question, where is my nucleophile? Yeah, one of these hydroxyl groups. Hydroxyls are not good nucleophiles. How could I make it a better nucleophile? Deprotonated. So I'm going to invoke some generic base. I'm going to call it B. Some generic base to deprotonate. Pro tip. In reality, this is very often histidine. We saw this in the acetylcholinesterase mechanism where histidine pulls a proton off to make that reactive oxyanion. We're going to see that again and again and again and again. It could be any base. There's lots of things that could go in there, but it's often histidine in real life. It's going to deprotonate, leaving us with that negative oxygen. And now we can look at our actual magic, which is an attack. Woo! Again, we've got a delta minus oxygen. We've got a delta positive carbon. We can see some bond formation and attack. Good so far? The way this mechanism will resolve, typically, is that when we add this new bond, this would be too many bonds to oxygen, sad day, we're going to swing electron density up into the oxygen. And we're going to end up with an intermediate state, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We're going to end up in an intermediate state that has an oxyanion! Woo! They're going to occur over and over and over again in practically every mechanism you're going to see in the rest of the class. So get used to them. Carbonyl comes up, forms an oxyanion. So we form this oxyanion transition state intermediate. Good so far? I see people writing, so I'm just going to stall for time. Good. Actually, I've never mastered juggling. Anyone here a good juggler? Because if so, I hate you. Not really. I'm very envious of you. Which is another pet peeve. People who say jealous when they mean envious. What? Envious is you want something else. Jealousy is you're scared they'll take what you have. Yeah, I mean, while we're speaking English. Okay, so once we form our oxyanion intermediate, we resolve this by reforming the carbonyl and kicking off a leaving group. This little OH minus that's then kicked off. Sorry, what? Yeah, the OH that gets kicked off here, boop, 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 this becomes an OH minus, could easily grab the proton, resetting the trap.
But as far as the OH being a good leaving group,
As far as OH being a good leaving group, it's not,
yeah,
but it's better than an ether.
yeah.
Ethers are even worse leaving groups. So you're kind of taking the best of the worst.
I thought ethers were better.
Oh, I'm sorry. Yeah, generically they are, but we have to assume some enzyme stabilization. Sorry, no, that's a great question.
Enzyme stabilizing.
We're going to help this guy leave, probably by giving it a proton to grab hold of. So in reality, I didn't want to complicate it too much, but let's talk reality. In reality, we'll probably have something crazy like a protonated carboxylic acid that is totally a great, alternative path. We saw this in acetylcholinesterase. So we can do that. But again, we'll go through that oxyanion, we'll form that nice ester linkage here. And that happens 3 times, and we build our triacylglycerols. Good stuff? Okay. Triacylglycerols are great for the body because they are incredibly energy dense. In theory, these pack together quite closely, and they pack with other triacylglycerol molecules quite closely. We can metabolize them for a whole ton of energy. The little comparison I like to keep in my mind is atom for atom, or molecular weight for molecular weight. Fats yield about 4 times as much energy as sugars. So they have lots of energy stored in them. And in the body, we just store them as big globs. Blah. In adipose cells, or in seed-type cells of plants, we have our cell, kind of this white border here, where we have a nucleus and some mitochondria and stuff, and then just these huge, ridiculous lipid drops. What's funny to me is this is actually not even drawn to scale. In reality, the lipid drop occupies much more of the cell. And you can kind of see it down here where lipid drop and that dark border around it is all the rest of the cell. See, there's like the nucleus is in that teeny bit right there. Like adipose cells are literally just a ball of triacylglycerols with a bit of cell wrapped around them. So they take up less space than carbs. And here's a nice little reminder. We have about a day of energy stored as carbohydrates in our body, as glycogen in the liver and the muscle tissue, whereas we have weeks of fat in the average person. It's rare to actually starve to death. You usually die of dehydration long before then. I mean, hopefully neither happens to you. But, if it's gonna, that's, So that's how we store lipids for energy storage. Good stuff there? Hit me, Cassie.
So stacking and stuff with saturated and unsaturated, like saturated is stacked more tightly. Does that have anything to do with like fats and like, does that affect at all how your fat droplets are?
Yes, absolutely. Absolutely, the degree of saturation affects your fats. But in general, in biological systems, we balance them. So beef fat, which is very similar to human fat, is about 45% unsaturated. And that's per triacylglycerol, but also per the large droplet. So you could imagine you'd have droplets where 2 saturated and 1 unsaturated, and then over here 2 unsaturated and 1 saturated, and they balance out to be about 45% unsaturated and maintain that.
You're not going to get like a dense.
Well, you do a little bit, yes. In a given fat droplet, there can be regions that are denser, and some adipose cells are denser than others, but not by a huge amount. We're talking variance of like 5 to 10%, not all or nothing. Yeah. Does that help? Good question. Yeah. It's actually a reminder of how good our bodies function, that we don't really drift from homeostasis much. Even in disease conditions, we don't drift too far from normal. 100% of anything is rare in biology. Okay, so we can store fats for fuel, but the other thing we do with lipids is make membranes of them. And just as a reminder, I showed a little graphic last time where I crossed out a whole bunch. There's all sorts of membrane lipids that we're not going to learn about, because that's the topic for Biochem 2 or graduate courses or other advanced stuff. We are going to focus solely on the glycerophospholipids and briefly touch on cholesterol. Sphingolipids are really cool, and we just don't have time to talk about them. Sorry. Wah, wah, sad trombone. So we're going to look at glycerophospholipids. And wow, that slide is really hard to see. I'm going to turn off the light briefly. Don't worry, you don't have to look at me now. It's much better. I like this, Rainey. You're good today. You're pumped. I like it. Whatever drug you're on, keep doing it. She is not on drugs. She's high on life.
She reacted way too fast to be on the drug.
That's true.
That was super responsive.
I think we can all attest if anyone's on drugs, it's probably me. So direct it the right way. No, I really love your energy today. I was not trying to pick on you. I love it. So, when we look at lipids, typically in a biological context, they're going to form bilayers, where we have polar head groups that have 2 fatty acids, forming a bilayer structure where fatty groups align together and polar groups are aligned on the outside of both surfaces. And what they look like is pretty much what we just drew, but just with one substitution. That is, they still have a glycerol core and 2 fatty acid linkages, but instead of a 3rd fatty acid linkage, they have some polar head group attached. And there's a variety of these polar head groups, and they're listed right here. Phosphatidic acid, which is what's listed here kind of, or phosphatidylethanolamine, which is if you had this, but then you put some other stuff on it. Phosphatidylcholine, which we've already seen choline before. Phosphatidylserine, so this R group over here now has a serine residue. Or phosphatidylinositol, which is where the R group here is some sugar. You'll notice that all of these have a phosphate attached. And if we wanted to draw and think about that reaction mechanism, it's the same darn thing, except instead of a carbon that's delta positive, we have a phosphorus atom that's delta positive. Still swings up and forms that oxyanion. All the jazz is the same. So importantly, these aren't that different. They are a glycerol linkage with 2 tails. The only difference is instead of a 3rd fatty acid tail, they have some kind of polar head group incorporating phosphate in the stuff we usually look at. That's a great hypothetical. I like hypotheticals, but I like reality more. So here's a real one. This, in fact, is the most common membrane lipid in your body. Approximately 60% of every membrane in every cell in your body is made up of this molecule. So this is the most common membrane lipid in your body and in most eukaryotic cells' bodies. And it's called phosphatidylcholine. And up here you can see our glycerol linkage, our ester bonds, and we have a 16:0. I counted really fast. No, I just know it. A 16:0 and an 18:2 delta 912. Common names, this is palmitic acid, and this is linoleic acid. So we have two fatty acid tails, one saturated, one unsaturated. And on the group, we have a phosphate group, followed by 2 carbons and that quaternary ammonium. This is called choline, this whole thing. That is the quaternary ammonium with the 2 carbon linker. This whole jazz is called choline. It occurs a lot in biological systems. So it's one of those things you just get used to seeing. Choline. This guy is incredibly common. It's in almost every cell in your body, usually in a high mass percentage. It also tastes really good. And you may have seen it in food, where phosphatidylcholine in food is called lecithin. I guess because phosphatidylcholine sounded weird. I don't know. Lecithin is a main component of things like butters or margarines, and it is also a major component of creamy things like ranch dressing.
How is that spelled on the left, the linoleic acid that starts with an L?
Oh, Linoleic. Sorry, that's an N. If you're, mentally challenged like I am, or handwriting challenged. Linoleic. Linoleic. My 5th grade teacher would be so disappointed. She used to say, "You have a tendency for your handwriting to go up," and I still haven't fixed it. Yeah.
Kind of side note, choline, that's also acetylcholine. Is it like just like a carrier molecule?
So when you take choline and combine it with acetyl, you get that neurotransmitter. When you take choline and combine it with this, you get that. It's just kind of a Lego block that's used in a lot of biological contexts.
Okay.
Anywhere, basically, we want an obligate positive charge, because it has no protons to lose, so it's just stuck as a positive charge. So it gets used in a whole bunch of biological contexts. As just like, there's a positive charge. Okay, so lecithin is used as a thickener and emulsifier in a lot of things like ranch dressing or Thousand Island dressing or that kind of stuff. And it's also a big component of our bodies. Yay. An area where you see this come up a lot is you will see in a lot of things like ranch dressing, soybean lecithin is a really common product you'll see in a lot of things. It's not dangerous. All it is they took a soybean and they scraped the cell membrane off and used the cell membrane of soybeans. Because it's the major component of soybean cell membranes, just like it's the major component of our cell membranes. Fun fact that probably will not ever be useful to you, but you never know. Archaea and bacteria cannot make this molecule. So it's a sure sign of a eukaryotic cell. If you're ever like, oh no, is this thing an archaea or a eukarya? It might happen, maybe. It's a good giveaway that you're dealing with a eukaryote. Or HIV, which wraps it around itself. Good stuff there? So membrane lipids, pretty simple on the face of them. What they do, again, is because of the fact that, don't worry about these micelles, because of the fact that they have 2 fatty tails and a polar group, there's going to be hydrophobic exclusion at play. The polar head group can interact with the surrounding water just fine, whereas the fatty acid tails cannot. They're going to be excluded by water and pushed together, and you're naturally going to form this bilayer kind of structure. The one thing I really dislike about these kind of depictions is they give you the false impression that molecular transport across a membrane should be easy. Look, there's all that empty space that things can push through. So here's a more accurate space-filling representation of that